Hello all, welcome to section 1.3, video 1. Here we're talking about vectors. So let's just talk about R first. R, this is a fancy R, stands for the set of real numbers, usually represented by number line. 0, we've got 1, we've got 2, we've got 3. Pi is somewhere over here, a little bit more than 3. Root 2 is a little less than 1.5, so maybe there's root 2 there. And the -1, maybe -0.5. And so on and so forth, forever and ever. There's our real line. Maybe indicate that it goes on forever in both directions. Boom. Yeah, R squared here is pairs. Yeah, sets of all things that look like a real number, comma a real number. So it's really the collection of all ordered pairs of real numbers. And this is, you've seen this a million times, I'm sure, in calculus class. This is represented by a plane. So our x1 axis, our x2 axis, and the point 1, 2 is represented by the ordered pair over 1 up 2. Where again, of course, ordered pairs, the order matters, right? 2, 1 would be over here. Okay, so these are maybe familiar already. In algebra, there's nothing stopping us from taking 1 or 2 or as many real numbers as we want and ordering them. So in general, for any natural number n, this is just a positive integer, we'll take r to the nth power to be the set of all ordered n tuples of real numbers, where n tuple just means, not double or triple, but n tuple. There's n numbers that we're holding on to in this set. And then maybe the first question that should come to mind, or does come to mind, is why should we care about this many things, right? The world we live in is maybe 3-dimensional, 4 if you count time. Why do we care about n dimensions? And that's a good question if we're talking about physical things. But we're mostly not. We're mostly talking about algebraic things. And algebra really do want to have n things floating around. In particular, each solution to a linear system in n variables is going to give us n ordered real numbers, the value of x1, the value of x2, the value of x3, all the way down to the value of xn. So we want some place for our solutions to linear systems to live, and they're going to live in Rn for some number n, R10, R5000, something. Okay, good. Oh, we should always be asking, why do I care? Even if it sounds rude, it's not, I promise. Okay, let's do a little more notation here. Right, an n by 1 matrix, that's one of these tall thin boys, n by 1. It's called a column vector. I put column in parentheses because we're not going to talk about row vectors until, for a long time. So if I just say vector, it's safe to assume I mean a column vector. And it's always useful to interpret these vectors as living in Rn. So for example, to distinguish a real number scalar quality from a vector quality, we'll put this little arrow over our vectors, unless we forget, and then we'll have to forgive ourselves. So the vector 2, 1 corresponds to the pair 2, 1 in R2. And this is true in Rn as well. Column vectors correspond to ordered n tuples. Okay, we say 2 vectors are equal if their corresponding entries are equal. And here, of course, order matters. Order matters. So the vector 1, -1 is not equal to the vector -1, 1. And also size and shape matter. So here's where we're talking about 1, -1. The column vector is not equal to the row vector 1, -1. Right? This is a 2 by 1 matrix. Technically, this is a 1 by 2 matrix. This isn't a matrix at all. This is an ordered pair. So if you're annoyed that these 2 things are equal, but if I put square brackets here and remove the comma, they wouldn't be equal, I'm very sorry. That's the notation. I take no responsibility. Someone else did this a long time ago. It's out of my hands. It's in the textbook. I'm not going to take any responsibility. So I'm sorry. We are going to distinguish carefully between row vectors and ordered pairs. These things are equal. But as soon as you change the parentheses and lose the comma, different things. So my apologies if it's confusing. Sometimes that's life. Okay. Good. Yeah, there are some algebraic operations that we can perform with vectors. Big surprise. So first, we can perform addition. If you have some vector in Rn u and some vector in Rn v, same in the same space. So both of these go from v1, v2 to vn. Both of them have n entries. Then we can add them just by adding them pairwise. The sum of these two vectors is just the vector you get when you add the first entry, add the second entry, and all the way down to adding the nth entry. What does this look like in R2? It's a great question. And yeah, what happens in general? In R2, if we've got some vector u here, maybe some little vector v, to get the sum of them, it's like you're grabbing one of the arrows and then dragging it over here. And so the resulting vector is what you get if you put the arrows end to end. So maybe let's do our best to try and move v over here, and the resulting vector is u plus v. This doesn't matter that you moved v over to u. You could have also put u here, and you get to the same place. So sort of like if you've got u and v, you can make a parallelogram out of them, and the diagonal of that parallelogram is the sum of those two vectors. All right. Scalar multiplication. I don't remember if we've introduced the word scalar before. It's just to distinguish between vectors and real numbers. So scalar is always going to be a real number for us. You can take more linear algebra later on where the scalars come from other places. I'll try not to talk too much about that. But for us, scalar just always means real number. You're supposed to distinguish numbers from vectors. Okay, so if we let c be a real number, a scalar, and we let u be some vector in Rn, then we can multiply u by c just by multiplying each of the entries of u by c. So this is called scaling u by the scalar c. And then geometrically in R2, and I'm choosing R2 here because it's the easiest one to draw. What happens in R2? If we've got some vector u again. I mean, we know what it ought to be. We know if we add u and u, it should be like taking a copy of u and putting it at end to end. So we know 2u is somewhere over here. Oh, 2u. And surely 3u over 2 is over there somewhere. This has got to be 0 times u. I guess our u should always have little hats on them. Hard to remember the hat sometimes. What's negative? Negative 1 times u. Well, it should be the same length of u as in the opposite direction. So it looks like the c times u is just carving out a whole line to the origin. Okay. Yes. There are some algebraic properties of addition and multiplication that should look very familiar. Nothing here will be surprising. It might even be so unsurprising, you might say, David, why even bother writing this down at all? I don't have a good answer for you. It is in the textbook, so I feel compelled to say everything that ought to be true about scalar multiplication and vector addition is true, but for the sake of clarity, this is what I mean. I mean that if you grab any vectors in Rn and any scalars, C and D, it doesn't matter which order you add the vectors. It doesn't matter, you can do u plus v or v plus u. It doesn't matter how you parenthesize them. You can do u plus v and then add w, or you can add w to v plus, or add u to v plus w. There's this zero vector where every entry is 0 and has the magical property of when you add it to another vector, you can just get back to your regular vector. Okay, and so on and so forth. there's this additive inverse to u called negative u, which is just -1 times u, with the property that when you add a vector with its inverse, you get back the 0 vector. Right. Multiplication of scalars to a sum of vectors is just it distributes like you expect it would. Similarly, if you add two scalars and then multiply with a vector, it's just the same as multiplying the vectors first and adding. It doesn't matter if you do c times the vector du or cd times the vector u, and the number 1 times u is just equal to 1. So all the algebra that you'd expect to hold for this for vector addition and scalar multiplication works. Nothing strange happening there. Okay, I'll see you shortly for video 2. Take care, everybody.